Good morning. We are going to be talking about logarithmic functions today. So the rest of the unit is going to be all based on logarithmic functions. And to start things off, we are going to be looking at what a logarithmic function is. It is a function of the form y is equal to a plus b ln x. That ln here is pronounced ln. It is a function that your calculator can do for you, kind of like sine, kind of like cos, kind of like tan. That L and then the N does not represent individual variables, but rather a function itself. Okay. In a logarithmic function, b can't equal 0, because if b was 0, this whole thing would be 0, and that wouldn't work for us. And a and b can be any real numbers. So what we're going to start off with is we're actually going to be graphing a couple of different logarithmic functions and then finding some information or some patterns that arise from doing so. So I have Desmos open here on the side, and I'm going to make it a little bit bigger. And we are going to start off with this guy here. So we have y is equal to 1 plus 1 ln, and we can either go and use the ln function here, or we could type in ln with our letters and get the same thing. When we look at this logarithmic graph that we want to graph ourselves, it kind of looks like an exponential but flipped off onto the side here. So there is this point here, our x-intercept, and we're going to graph a couple of different points. So why don't we graph when x is 1, when x is 4, and x is 7, just to get some sporadically placed points here. So we'll graph all these guys on our graph in our notes, and then we'll kind of connect the dots there. So looking over here, so we have to draw in, first of all, our scale and label our axes here. So this is 1, 1. Now that we have that, we can plot the point. So we have our x-intercept of 0.368. So that happens-ish over here. We have the point 1, 1. We have the point 4, 2.38. So 4, 2.38. And 7, 2.96. 7, 2.96. Okay. We could go ahead and kind of connect the dots to mimic the shape as best as we can. So do your best to go ahead and do that. Oh, I don't want to straight line. And on the other side, we have our graph approaching our y-axis. But if we zoom in with Desmos, we could see that it's not actually touching. And we could scroll down and down and down and down and down on our Desmos, and we could see that it's might be getting closer, but it's not actually going to touch at any given point. Okay? So just like we had a horizontal asymptote when we were talking about exponential functions, here we have a vertical asymptote because our graph won't ever touch our y-axis. Okay, so again, it approaches but doesn't touch. All right, so we can examine our domain, we can examine our range, our x-intercept, our y-intercepts, our end behavior, and all of that jazz. And we're going to go ahead and do that now. So from our domain, since it never touches the y-axis, but it approaches it, we can say our smallest x value is 0, but 0 itself is not included, right? Because it's never going to touch that y-axis when x is equal to 0. And it continues on, and if we go and look at our logarithmic function on Desmos, we can see that it continues on forever. Of course, we are not going to draw infinity because it would take us our whole lives. But we can draw the arrows at the end of our graph. Our range, however, that's bottoms up. So we're starting from the bottom, which is negative infinity, and it continues to go upward forever. Right? So if we're looking at this guy here, yes, the arrow is pointing to the right, but it's pointing to the right and slightly up. So it is going to eventually get to infinity. For x-intercepts, we have one of them, right? And that happens right at that point there. So when x is equal to 0.368, or at the point 0.368 comma 0, right? You could write down the x-intercept in whichever form you prefer. However, we do not have any y-intercept, right? We have that vertical asymptote. So instead of writing y-intercept, we often write does not exist, DNE, right? We can't write 0 just like we couldn't write 0 before, because that implies we have a y-intercept at 0. Our end behavior, right? When we look at our graph, reading it from left to right, it starts down here in quadrant 4 and ends up here in quadrant 1. So our end behavior is quadrant 4 to quadrant 1. And we have no turning points. This graph here is always increasing, right? It's increasing pretty rapidly at the beginning through this point here. It's still increasing, but it slows down the rate at which it increases at. But it's still always increasing and doesn't turn around. All right. We can do the next graph as well here. So before I even start doing anything, I'm going to put in my scale. I'm going to label my axes. And then we can get things going here. So here we have y is equal to -2 plus 5. And like I said before, you could type in ln with the letters. It will automatically recognize that we're talking about the function ln ln rather than the letters ln. Whichever is easier for you, you can go ahead and do. And we are going to do the same thing. We're going to plot some points and see what happens here. So we have the point 1 comma -2. So we could go ahead and plot that. We have the x-intercept at 1.492. We have, when x is 4, y is 4.931. 2, 3, 4, 4.931. And when x is 7, y is 7.73. We don't really have room for that on our graph here. But we know that it will continue on. So we could, just to kind of give us an indication of where that line continues to, draw on that dot there if we wish. Then we can kind of connect the dots, kind of mimic that shape as best as possible. Oh, hold up. I think I drew my point in the wrong spot here. This should be higher. This should be almost 5, so this should be up here. That looks better. Alright. So we are connecting our dots with this nice, smooth curve. And on the other side, again, same idea. The graph approaches that y-axis, but never touches that y-axis. We want to make sure that it continues as a smooth curve. And try your best to make it like one continual thing. All right. So there we have our graph. Same thing, we're going to go through our domain, our range, all of that jazz. Our domain is similar to our last graph, where it starts at 0 but doesn't include 0 and goes all the way to infinity. Our range, same thing, starts from -infinity all the way at the bottom to +infinity all the way up. We have one x-intercept, and that occurs when x is 1.492. Or we could write it as a coordinate point, 1.492, comma 0. We have 0 y-intercepts, which means they do not exist. The end behavior, same as before. It starts, as we're reading it from left to right, it starts in quadrant 4, and it continues to quadrant 1. And there are 0 turning points. So, taking a look at these guys, a couple of things that you might have noticed. These two specific points, 1, 1, 1, -2. You might have noticed a little bit of a pattern, or maybe you have a hunch that a pattern is coming on, but you might notice something about our A values and our Y coordinate when we have our X coordinate as equal to 1. Okay? So maybe we'll see if that pattern kind of continues on our next graph and see what happens. All that we can say for sure is between these two graphs, both graphs are increasing. Their Y values are getting larger, or getting more positive as we move from left to right across the x-axis. Perfect. We're going to do the same thing here with these next two graphs, but notice that the next two graphs, our B values are negative. Right? In our first two graphs, our B values were positive. We had +1, we had a +5. This time we're going to be graphing things where our B values are negative. All right, so we're going to go ahead and get cracking here. So we have 8 minus ln x. Oh, sorry, 6 minus 6 minus 8 ln x. Minus 8 ln x. There you go. And we're going to take a look at some of these points. Oh, it's +6. My apologies. There you go. 6 minus 8 ln x. Whew. So we have that point there. We have 1, 6. We have an x-intercept. And we have some points here that we could go ahead and graph. A few of them that we can. So let's get started. Before we do so, we have to make sure we indicate our scale and label our axes. All right, we've got the point 1, 6. 1, 2, 3, 4, 5, 6. We've got the point 2.117, 0. That's going to be ish there. We have the point 4, -5.09. And our next point there is going to be off the graph. Okay. We could see as we get higher and higher up here, again, it is approaching the y-axis, but not touching the y-axis. Okay, so we still have that asymptote that exists, but now we just have our graph approaching it as our y values get larger rather than get smaller. We can connect our dots as best as we can. Get a shape that looks something like that. One of those points that you might notice a pattern from before, we have 1, 6, right? That 6 looks like it's coming from our A value there. And we can examine our domain and our range as well. So here we have our domain, same as before. The smallest value of x is 0, but 0 is not included because we have that vertical asymptote. And it goes all the way to infinity. Our range, starting from the bottom and moving upwards, we have -infinity to +infinity. We have one x-intercept, and that occurs at x is equal to 2.117, or at the point 2.117, 0. We have no y-intercepts because that's where a vertical asymptote exists, which means our y-intercepts do not exist. Our end behavior. Remember, when we're looking at end behavior, we're looking furthest to the left from furthest to the right. So if we start from the left, it's actually starting in quadrant 1, and it's ending in quadrant 4. So we have Q1 to Q4, rather than Q4 to Q1. Okay, so they're using the same quadrants, but the order of them matters. We're always reading it from left to right. And turning points, there are none of those, guys. It's always going to be decreasing as we move down the graph, or if we move left to right across the graph. So as as we go left to right, going down, 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 down. Alrighty. We've got one more graph to go. I think at this point we could probably predict at least one point on the logarithmic graph, and that's where our a value is. So if we continue on the pattern, we know that that a value will occur as a y coordinate when our x coordinate is 1, so we have the point 1 comma negative 3. So we could predict that to be there. Everything else, we can't really do a lot of predicting with logarithmic graphs, but at least that one point we can. So we have negative 3 minus 2 ln x, and of course, there we go, we are correct in this case. Okay. We have some other points that we can plot. So we have 0.223 as our x-intercept. We have 4 comma negative 5.773, so 4, negative 5.773. And 7, we have negative 6.892. Somewhere there. Okay. Of course, we need to make sure that we label our scale and our axes. Can't forget about that. And then we could connect our dots as best we can to show the graph. Alrighty. And again, we do have that point that we predicted that involves our a value there, which is kind of cool. Alright, our domain, same as before, we go from 0 to positive infinity. Our range, no surprise, negative infinity. Oh, that should be a soft bracket. To positive infinity. We have one x-intercept, and that occurs at 0.223, or at the point 0.223, comma 0. We have no y-intercepts, which means they do not exist. Our end behavior, as we read it from left to right, it starts in quadrant 1, ends in quadrant 4. And there are 0 turning points. What you might notice about these two graphs is both of these graphs are decreasing. Right? As we go from left to right across the graph itself is going more and more negative. Right? The graph is moving downward in terms of our y axis, or y values. So, we're going to do a little bit of analyzing of the graph just to see what patterns we noticed. So if we're looking at our a value, how did our a value affect the graph? Well, we know that, I'll use a purple here. I'm going to close Desmos. We're not going to use it again for this lesson. So how did the a value affect the graph? Well, the a value shifts the graph up or down so that it intersects the point 1, comma a. We will always have this point on our graph, right? 1, comma a, and we could have that point regardless. Keep in mind, if we have a graph or a equation that is just y is equal to b ln x, that implies a is equal to 0 in this case. So we will have a point at 1, comma 0. It'll happen to be our x-intercept if that is the case. Okay, so even though you might see an equation where it just looks like b ln x, that a value still exists. A is equal to 0, which means we'll have that point at 1, comma 0. That's just a little bit of an aside there. Our b value, we noticed that in our first two graphs, our b value was positive, and the graphs were increasing. And the last two graphs, our b values were negative and the graph was decreasing. So to write that down, if b is greater than 0, so b is positive, then the graph was increasing. And our increasing logarithmic graphs look like this. Oops, maybe that wasn't the best try. Similarly, if b is negative, it's less than 0, the graph was decreasing. And a decreasing logarithmic graph starts upward and ends like that. So logarithmic graphs are similar to exponential in the sense that their shape is very, very similar, but they are just kind of translated or flipped over to be in a different position. So just like our exponential graphs had a horizontal asymptote, our logarithmic graphs have a vertical asymptote because, again, the graphs are similar in shape, but they're just kind of flipped over to the side. So just like we did in exponential graphs, we are going to look at some kind of key points of a logarithmic function. So our domain is always going to be, unless we have a word problem where context matters, we have 0 to positive infinity because we're never including our y-axis when x is equal to 0, so we use that soft bracket there. Our range is always going to be unrestricted. It could be negative infinity always to positive infinity. We'll always have one x-intercept, but 0 y-intercept. For our end behavior, if b is positive, it's a value greater than 0. That means it's increasing, which means we will start in Q4 and end in Q1. We'll start in quadrant 4 and end in quadrant 1. If b is less than 0, that means it's decreasing, looks like this. Then we're going to start in quadrant 1 and end in quadrant 4. Remember, with our end behavior, we are looking where we started to the furthest left and where we're ending when we go furthest right. And there's never going to be any turning points. Okay, so if we want it kind of in pictorial form, if b is greater than 0, the function is increasing. And increasing is going to look something like that. And if b is less than 0, it's negative. That means the function is decreasing. Oops, that's kind of bumpy. And it's going to look something like that. Of course, the shape shifts a little bit with the numbers that we use, but the overall pattern of what that line looks like is going to be similar. All right. But the one thing that you might be noticing when we're looking at this guy here, so if b is positive, it's greater than 0, then it's increasing. If b is negative, it's decreasing. But what happens when b is equal to 0? Well, if you remember from the beginning of our notes today, we said that b cannot equal to 0. Because if b is equal to 0, 0 times whatever ln x is will be 0. And it won't result in a logarithmic function. So b cannot equal to 0. That's why we don't address it when we're talking about increasing or decreasing, because it won't provide a logarithmic function. Alrighty, that's it for today. You have a little bit of homework to do, and then we'll catch up again for 8.5. Adios, muchachos!